And well, as we know that the core supply the heat of Earth, which generate the mantle convection, and mantle convection drives the plate tectonics, redistributes the heat, and the circles chemical species. So if we can constrain the spatial temporal changes in the
Ben, could you hear me?
Yeah.
Please go back to the.
Okay.
I could add a little bit. To your cover page. To your cover page. Okay. So there are 4 authors. The first one currently he's postdoc at Colorado State University. So he's going to give a talk on Wednesday. And I forget what's the N stands for. Let's say N White is his PhD advisor at Cambridge. And they are so for White, for his own research that he's interested in looking for the patterns of mantle convection. So with the idea that if the mantle convection goes, then it will have the vertical consequences. So this mantle convection probably is not perfect as what we would do on in our mind. So vertically, it's going to have some differences. So basically, he combines a lot of some of the geodynamic modeling and also some natural observation. For example, in particular, paying attention to the marine sediments, because by the surface subsiding or upwelling on the surface topography, that will lead to different sedimentary phenomenon. So they have been working on that in different continents. So the second author. And the third author, I think he's a geochemist. So he does a lot of work in geochronology. And the very last author is a geodynamist. So basically, it's a combination of geophysics and the geochemists working together. And but for the PhD students, well, his PhD advisor, that both of them are, well, like I say, they themselves are lying something between. Okay, so Ben, go ahead. Please move to the third slide and then go on.
Okay, so if we can constrain the spatial and temporal changes in the thermochemical structure of the mantle, it will help us to refine our understanding of this interlinked phenomenon. And there are 2 well-established way to investigate the thermochemical state of the mantle, which are igneous, geochemical, and seismic tomography. But the important difficulty is that composition of the partial melts within the mantle and the shear wave velocity of mantle rocks are both sensitive to the combined effects of temperature and chemical composition. So by analyzing the distribution of the composition of volcanic rocks in conjunction with shear wave velocity anomalies, it is possible to determine temperature variations within the upper mantle. And this paper's principal aim is to quantitate the relationship between the composition of volcanic rocks and mantle seismic velocities with a view to constrain the size, extent, and the surface expression of putative thermal anomalies. But they are less concerned with the more difficult problem of how these anomalies are generated in this paper. And the data what they got include 2 parts. First is the more than 20,000 geochemical analysis of neogen to quaternary interplate volcano rocks, which is the geochemical data. And the other part is the geophysical data, include the delta velocity and lithospheric thickness and the potential temperature from this SL tomographic model. And the delta velocity is the average value of the shear wave velocity anomaly. And they show their data on this called model weight projection map. It is kind of unfamiliar for us, so I'll introduce a little bit. So this middle one is the North American and South America, and the left one is the east of the Asian and Australia, and the right part is the sorry, this is west of Europe and Africa, and so the yellow circles on these on those map is the location of the intraplate magmatic samples less than 10 million years, and located less than 400 kilometers from locus of the eruption based on the present day plate space. And you can see it's clear that the interplate volcanism is concentrated within the regions where the negative shear wave velocity anomalies occurred at depth of 150 kilometers minus and plus 25 kilometers, and that interplate volcanic rocks are concentrated within the region where the lithosphere is less than 100 kilometers thick. And this is the overview of the methods. First, they examine the correlations between the distribution and the composition of neogen to quaternary interplate volcanism and delta velocities and lithospheric thickness. Secondly, they estimate the potential temperature and lithospheric thickness using a combination of geochemical and seismologic and techniques. And finally, they check the link between the interplate volcanism and the distribution of emergent marine sedimentary deposits, which are a tangible manifestation of the dynamic tomography uplift. So for I started for easier calculation and comparing with the geochemical data, they process the data by binding the into one latitude multiplied by one longitude, which is the this sigma A. This sigma A means average value of delta velocity at depths of 150 kilometers, where the global is subdivided into one latitude multiplied by one longitude and weighted by the latitude. So you can see there's 89% of the sigma A occurs in the region underlined by negative values of delta velocity, whose area distribution only constitutes 61% of the global area, and there are 95% of sigma A occurs in region underlined by continental lithosphere less than 100 kilometers thick, whose aerial distribution constitutes 62% of global area. So they want to say that this phenomenon is not just a coincidence; they are related. And then they made this figure 3 to explore the correlation, to explore the relationship between the tomography and geochemistry. Before that, they did some data filter exercises, all the samples that have MgO contents less than 9 weight percent and more than 14.5 weight percent from database to ensure that only retain samples that are close to the composition of the primitive mantle mouse. And R in this diagram is the Pearson correlation coefficient, and the P is the population correlation coefficient, and the N means the number and the range of the beans. And they use the this LA-SM ratio, because this ratio concentrates this ratio of the LA and SM concentrates in magnific igneous rocks is often used to track mantle melting. So the relationship between the LA-SM ratio and the delta velocity at 150 kilometers is a useful way to explore the role that the subplate thermal anomalies play in generating interplate volcanism. And since 96% of our beams occur where laser ferric thickness is less than 100 kilometers, they use the average value of delta velocity at 150 kilometers depth to represent the asthenospheric mantle. The result is that the igneous rocks with lower LA-SM ratio, which are indicative of higher melt fractions and higher temperature at this depth. In figure D, they use different tomography models. This result shows same pattern that correlations between LA-SM ratio and delta velocity are observed at depths at 150 to 200 kilometers, where the influence of laser ferric thickness change is seem to be negligible. So it is reasonable to assume that the correlation between delta velocity and LA-SM at this LA-SM ratio at this depth are principally controlled by the temperature variation within the asthenospheric mantle. And in this slide, they use the PCA to analyze their data. The composition of the mantle source region also reflects the value of both LA-SM ratio and the delta velocity. So to determine how the thermochemical structure of the mantle controls the melt composition, they use this PCA to analyze on a suite of 8 incapable elements concentrations, which are taken from the filtered and binned version of database. And they also construct a synthetic data set from this called INVMEL model. And they use this model for range of temperature, potential temperature value, laser ferric thickness, and mantle composition to calculate the element concentrations. So both natural data and the synthetic data shows the same PCA pattern, and they compare the PCA results with the data they have. It shows that the PC1 is here. PC1 is positively correlates with both LA-SM ratio and the delta velocity. You can see here this positive correlation, and here, and there is a negative correlation with the epsilon ND. This value, the epsilon ND, is a commonly used proxy for the mantle depletion, because the depleted mantle has higher value of epsilon ND than the fertile mantle. So they conclude that the PC1 is sensitive to melt fraction variation. So after that, for calculation the asthenospheric temperature, there is a geochemical model called INVMEL-V20, which is used to calculate the REE concentrations generated by mantle melt for different values of potential temperature and lithospheric thickness. So the vertical axis in this figure is the average RE concentrations normalized with respect to the source composition. The value is produced by this model, and melt fraction plots as function of depth. This red curve line is melt fraction calculated by fitting observed RE concentration in panel A and D. And this misfit between observed calculation RE concentration plot as function of potential temperature and lithospheric thickness, where the color scale of RMS value. So the RMS value is lower. When it's lower, it means the data produced by model is more like the observed data, which is real data. After they got the inverse geochemical data model for calculating the temperature by RE concentration, they calculate all of the data's temperature by this model. And there's a positive correlation of R equal to 0.54 between geochemical potential temperature and the tomographic estimates of the delta potential temperature, which is the temperature anomaly with respect to the ambient asthenospheric mantle, which is the 1312 and 1333 for both model. They assume that's the asthenospheric mantle's temperature. And in order to highlight the consistency between geochemical and tomographic estimates of the mantle potential temperature and lithospheric thickness, they present a transect that summarize regional variation of LASM ratio delta velocity at depths of 150 kilometers, delta temperature at the depth of 150 kilometers, and the lithospheric thickness across from Europe to Africa. So the next slide is this transect. And they propose this mechanism for generation of interplate volcanism is rapid large-scale uplift. This prediction is easily tested by examining the relationship between the tomographic evaluation and emergent marine sedimentary rocks that crop in region where interplate volcano predominance, which means where asthenospheric temperature and are anomalous high and where continental lithosphere is anomalous thin. So they found two examples from this model. There's this two blue square is present the lithospheric thickness estimated from the evaluation of the marine rocks by assuming combination of the lithospheric mantle thinning. Yeah. And the conclusion is that the positive asthenospheric temperature anomalies and the thin lithosphere are closely relative during Neogen and the continental types. And the removal and thinning of lithospheric mantle produce regional uplift, but substance will eventually occur as the lithosphere conductively cools and rethinkens. And finally, by combining the distribution and the composition of interplate volcanism with calibrate tomography models showing that asthenospheric temperature variation and lithospheric thickness change can make a significant contribution to dynamic tomography. Yeah, that's all. Thank you.
Okay, thank you, Ben, for leading, for making the presentation for us to show the paper. now it's time for us to discuss your doubts, your concerns, and you can open your mic, or you can also leave leave the message in the chat if it is inconvenient for you to open the mic. So go ahead.
Hi Ben, just have a quick question. So I'm just wondering, is this an interplate or intraplate? It's intraplate, right? It's within the continent.
It's intraplate. Sorry.
Intraplate.
Yeah, it's
okay,
intraplate.
Okay, it's interesting because if you go back to figure 1, where you show the distribution of all the chemical composition, a sample location. Not figure 1, sorry. The map figure slide 5. Yeah. Yeah, I found there are quite a few samples that fall within the ocean, right? A lot of them are actually not really intracontinental setting, or based on my understanding. For example, there are like, I don't know, like in the like western coast of South America, there are quite a few.
Yes, right.
It's in the Pacific Ocean, so yeah, maybe you can ask, or we can ask the author later. So how they define, the sample location. Some of them are clearly fall within the ocean.
Yeah, I think in their paper that they state that it's like 400 kilometers away. Maybe I had the wrong recollection. Because in this confusing because
yeah, a lot of samples are actually far away from the continent, from the coastline.
Yeah,
or it's a setting. Maybe the intraplate means like can be oceanic plate.
Yes, the ocean plate. But what I think that they mean is far away from plate boundaries, so that doesn't mean subductive zone. I think, or more, for example.
But the North American, like western coast of North America, there are quite a few samples as well, which are very close to the subductive zone. Similarly, Western Pacific near Japan, right?
Yeah, I think we could ask the speaker on Wednesday.
Okay, actually, I think the more general question is it possible to find the samples, like those kind of volcanic rocks, within the continent, in the Cratonic region?
Of course, there are, previously there were large provinces. I think the basic idea is that, okay, somewhere that has higher temperature, once it's above the temperature of the solid dust peridotite, then the melt generates. So I think if we take a very naive and a simple idea that's how it comes through. Yes, within the continents, there are parts that are slightly harder, and then we do have the mantle melts or basalts generated. So yes, they are. If I'm right, then
part of the region because it's a neogen to quaternary, right? So they have the temporal, like temporal range.
Yeah. But I think, if this is so new, I'm not sure. Daishan qualifies, for example. Definitely it's a neogen quaternary. But I don't know.
Okay, they use a relatively new samples, young samples. I think part of the reason because they would like to compare it with seismic observation, and the seismic observation they mainly reflect the current, the mantle image, the mantle status. So make sure they are actually comparable, like geochemical data and geophysical data, they are comparable.
Yeah, I think
at least both of them are reflecting the kind of relatively recent tectonic events.
Yeah, I think that's what the paper is trying to say. I think on recollection, because the paper probably state that they want to choose the young samples that by the plate velocity, they move less than 400 kilometers away so that they can be trackable. But we could ask the speaker for clarification if the speaker doesn't mention this part. So go ahead.
Yeah.
Okay, I think I think they didn't explain more about why they choose they just say that these two elements are sensitive to the metal melt condition.
Is this a typical element ratio used in geochemistry by geochemists or physiologists? I'm just wondering. Is it LASM ratio? Is this like typically used by the, by you guys?
Actually, LAYB is more commonly used.
Yeah.
Okay. It's quite surprising to me, the correlation between the scientific velocity and this ratio. It's really good. Like if you go to that scatter plot.
Yeah.
Yeah.
Slide 7. It's surprisingly good.
Got it.
Yeah, because in the review, if the reviewer's comments, which I sent later by email, which is very long, there's 91 pages for three rounds of review. Actually, the reviewer said that it's a little bit surprising to see that. Actually, it's okay. I mean, it's not perfect, but it's pretty good. Actually, what also strikes me is that when they did a PCA, for example, the principal component 1 contributed 79%. So that means really a lot. Actually, in geochemistry, that I think is pretty hard that you find the primary principal component that is so high.
Yeah, true.
I'm just wondering, is it possible for you guys to systematically search this kind of chemical ratio, element ratios, and to see which one correlate well with the scientific velocity? Is there any even better one? This LASM. Could there be an even better one?
Yeah, Ben, go ahead.
I don't know. Maybe they just choose the best one is the LASM. Maybe the LAYB is not good as this LASM result. I think so. I think that.
But you guys have all this kind of element ratio, right? So maybe you can look at some other element ratio and to see which one works the best.
Yeah, sure.
Yeah. Anyway, it's quite surprising to see.
Yeah.
So I think they have already tried all the proxies and then they pick up the best one.
Yeah, that's
possible. Yeah. Oh, okay. Maybe I ask another one. So there's like a code. It's called MEL-IN or something, right? I think you showed in one of your slides. MEL-IN. I think probably means stands for a melting version or something.
Okay. Let me find that.
Or IN-MEL or something.
Okay. I am.
It's
this one.
IN-MEL model. Yeah, go back. IN-MEL model. Yeah, IN-MEL model V12.
10.
Is this a fine? You can stay here. Yeah, this is an IN-MEL V12, right? I'm just curious. Like, is this a package, right? It's a software package. Is it developed by geochemist or by geophysicist?
Dan Keynes. So he's everything. So he wrote the paper of plate tectonics in Nature in 1986. And when he was postdoc at the Scripps Institution of Oceanography in San Diego. And then when he moved back to Cambridge and dominated the department for the next 50 years, he worked on all sorts of different things. So although he was a geophysicist, but he also worked on the geochemistry too. So for this one, I think it's, I didn't know the detail, but I would say that it's a geochemistry code. I don't think it's written in Python. For some old person like Dan McKenzie, I would bet
yeah.
Right. In Fortran is very low.
Okay.
Okay.
Yeah.
Yeah, I can see in the acknowledgement, McKinsey generously provided software for in-mail forward model. So it's not open source for sure.
Yeah. And they only explain some equation on their method part, but I think this part is not available code.
Yeah, that means like it's difficult to reproduce their results. But anyway.
So the R means the Pearson correlation efficient, right? So it can be negative number. It can be a minus number. So it means the negative correlation with these two data or two things. It can be positive correlation. It can be a negative correlation, right? So it can be so the R can be minus number.
Yeah, if they are perfectly linearly correlated positively, then it's +1. If they are perfectly negatively linearly correlated, then that's -1. In the real case, most of the time is lying somewhere in between.
Oh, another question, Ben. So they estimate the melt fraction based on the geochemical data, right?
Yeah.
The percentage of melt. So did they
Yeah.
show a map of that?
Show what?
The map of melt fraction or melt percentage.
No, I think no, because I don't know why they didn't show the map, but in this figure they just I think this figure is made by the data of their model produced, not the real data. So maybe
What
this
about
is
the
not
next one?
Yeah. Yeah. Okay.
What about 11?
Yeah.
What's this map? What this map shows?
It shows the temperature.
The temperature. Okay.
Anomalous temperature. Like.
Okay. But they mentioned melt fractions inferred from volcanic rock compositions, but they didn't show like the actual melt fraction.
Yes, right.
And also this is like a global distribution of temperature, right?
Yeah.
But they only have volcanic rocks at certain locations, so I don't know how they got the temperature for the entire globe. Or they integrate the seismic.
Yes. I think that only the you can see the circle. They also got the color. So the circle is the volcanism data, and the global is is colored by the seismic data, I think.
Oh, I see. Okay, I see. So the left figure is actually the kind of a comparison.
Yeah, right.
Okay. delta TP. Oh, okay, from two different methods. Okay,
Yes.
I see. Mm.
So, but through the mineral pairs that you're working on now, do you think that you could also get this temperature?
Yeah, I was thinking that, but this paper's method is kind of complicated. So if maybe I can go back to this paper they reference in the reference. So, but I didn't check the detail, but so maybe I can find more in this original paper that matter from.
Paper they did database.
Yeah.
So without an analysis, they did provide an Excel spreadsheet. Actually, I sent it in an email that we could take a look at.
Yes, this data Excel.
Yeah, it's in Excel. I sent it in the email. It's in their supplementary. So they have all the raw data there.
Yeah. I got that. Yeah, and yes. So,
still that they have to make certain assumptions about the bulk metal composition, right? So here they are, let's say there's average metal composition, I think, because otherwise they won't be able to get the melt fraction or temperature. Because for example, you will have extremely depleted metal somewhere, then it's very hard to melt that depleted metal because you have every mineral is very hard to melt. But these have a very fertile mantle that is much easier to generate and melt. So basically with the same temperature in position with depleted mantle, we won't generate any melt, but in position, in a location with a fertile mantle that with a lot of CPX, for example, then they are going to generate melt. So although the seismic velocity will be different in two different places, but their temperature are exactly the same. That could also be. So for this paper, actually, I forgot their argument because I think in the review, probably people have talked about it. Is that so how they are dealing with the composition? So how they are dealing with the composition differences in, like say, mantle composition heterogeneity in the mantle?
The hydro. I think
the bulk metal composition are different in different places. So how do they deal with that? Otherwise, if the compositions are different in every bin they are using, by every bin I mean 0.5 degrees. I think that's how they made a bin. So yeah, if composition everywhere are different enough, then they could not directly compare temperature, at least calculating by geochemistry results.
Yes, that's right. I forgot to. I forgot how they solve this problem.
But they didn't use the bulk composition, right? They only use REE. like inverse modeling, like in figure 4, it only shows the REE, right? So I'm not sure if they considered like. Okay, maybe they didn't consider the bulk composition.
Here they say that the inverse model assume a uniform this rock type source and does not consider the other type of the rocks, mantle rock. In the same page, in the 7th page. They are saying that there's some limits of these, both of the geochemical model and this geophysical model. So the disadvantage, one of the disadvantage of this geochemical model is they didn't consider more of the other types of the bulk mantle composition, I think.
And how did they get the depth constraint from geochemical data? Like those volcanic rocks, how did they know the source depths?
The source depth.
Yeah, where those volcanic rocks come from, like the depths. Oh, is it possible to get the depths from geochemical data?
I think they well, I think this
or maybe they did only assume it's coming from sublithosphere, like from sublithospheric depths.
No, I don't think so. I think they can get the depths from this this model, right? This this
from research. Okay. From the inversion.
Yes.
So essentially, this kind of a pattern in REE elements, they can tell you the depths, or they have some depth information in this REE.
I don't think so, though. I don't think so. They can tell you the depth. I don't think so. From seismology. Because if you want to find a barometer, I don't think REE is used for any barometer. REE are only used as a thermometer.
Yes.
Okay. But they are searching two parameters. One is potential temperature. The other is the lithosphere thickness. So they got some like depth information from the observation, which is REE.
I think they have the information. I think they want to say it is a potential temperature. Then they assume that that temperature is at a asthenosphere lithosphere boundary. That's my interpretation for it.
Okay. Yeah, I gotta look at the method section. There's quite a bit of details here.
we can also leave this. We will take a look at this later on, and we also speaker on Wednesday. Any other questions now? Comments? So for the first author and his advisor, they are interested in the vertical movement of the plates. I think that's the main reason why they are working on this. Although the N.J. White that himself is more interested in different types of sediments, looking at those sediments to trace the vertical movement of the plates. So for this one, it's more like from a magnetic perspective, they want to look at the upwelling process. Because in the end, that this melts, so that must upwell from the mantle to the surface. Contrary to what we thought about it before, that but to me that is still lacks in the reviewer's comments, that one of the reviewer that the reviewer number one was really debating with them in terms of the large low shear velocity provinces that the signals from deep mantle, from lower mantle, and the author that claimed that for this paper they don't care about deep mantle. They say even you have deep mantle source, in the end they still need to generate a melt in the shallow part, so that we have the intraplate volcanism and with the S velocity. So for here, that to me that this S velocity, to a certain extent, that it is still like a mantle plume idea. To me, that let's say that of course they are not exactly the same, but I think the idea has a lot of similarities. Is that they do have the higher temperature local regions here and there, and then generate some melts and produce the intraplate volcanism. But where does the heat come from? So it's very likely that the heat still comes from deep mantle. Although maybe the components, the intraplate volcanism magmas, they probably could still come from upper mantle, or they could come from deep mantle according to some noble gas evidences, for example. But I think they don't need that. But still, it's not necessary to have the deep earth geochemical components, but you need some deep earth heat. You still need the heat flow from the deep earth to generate this temperature anomaly. Otherwise, how does this temperature anomaly coming from? Because they are, as they claim that they would try to get the intraplate volcanism that should be far away from any subduction zones or plate boundaries. So to me, first, it's not too surprising that you see the intraplate volcanism regions where they have low shear velocity. That shouldn't be. So to me, that the highlight of this paper is that they found a correlation about LASM ratio correlation, which, let's say, different reviewers might have different interpretation, but in the end, that is still interesting observation that they could make find through the data. And looks like this correlation is very strong.
Do you guys have more data? LASM. They collected how many samples? Like 20,000 samples or so, right?
Yeah, 20,000, but not all have the. I think not all have the LASM. There's 17,000 LA and 14,000 SM. I think it at most 14,000 LA SM ratio.
Okay. How about in your database? You have a much larger database, right? This is from GeoRock, but
Yeah,
except
yeah,
for GeoRock, you collected a lot more data from the literature.
Yes, and it's the rock data is larger than the mineral data. I think it's bulk rock. It's basalt or something. And in the paper, they didn't say their data is from GeoRock, I think. Didn't mention that.
They mentioned acknowledgement. Database 1 was compiled with the aid of GeoRock database.
Oh, right.
Okay, but they might have some other data from other sources as well.
Yeah.
Yeah, I think so far this is the best correlation I've seen between geochemical and geophysical data.
Right. Yes.
Yeah, worth looking into other elements ratio. Maybe you can find an even better one. Yeah.
Okay.
Okay, we have lasted for about 1 hour, and thanks everyone for your participation, and thanks Ben for leading the discussion. So we are going to see the speaker on Wednesday, but it will be in the morning in Beijing time. Okay, have a good evening, everyone. Bye-bye.